Hello and welcome to another review session for your final exam in Calculus 3208, brought to you by CDLI. And today in this session we're going to be looking at finally getting into some calculus with this inverse trig business. So we're going to be taking the derivatives of the inverse trig functions. And with regard to that, the first thing we're going to do is we're going to compute the derivatives of the three basic inverse trig functions, inverse sine, cosine, and tan, and we're going to compile a table of derivative formulas for all 6 inverse trig functions. So we'll actually be computing the other 3 as well, but you'll see how we break this down a little bit differently. So let's have a look. So when we go after or find out what the derivative is for an inverse trig function, we're going to use a method here. And this is the method that we don't really look at much in this course, but I think it helps us if we look at it to see how this stuff comes together. So in this course, what we do is we sort of use the method without talking about it. But what it is it's kind of a sneaky way to get at the derivative of an inverse function. So let's say I want to take the derivative of a function y, okay, and I don't know if the derivative of y equals f inverse. I don't know what that derivative is. But I do know how to take the derivative of the original function f of x. Then what I can do is we know that an inverse function is just what we get when we switch the variables. So if I switch those variables back and I look at f of y equals x, so apply f to both sides if you want and cancel it out whichever way, and then use implicit differentiation. So what I get from that is f prime of y times dy over dx, and that's equal to 1, because the derivative of x, of course, is just 1. So then it says divide and substitute. So all I have to do is take dy over dx is going to be equal to 1 divided by f prime of y. But remember that y is, of course, going to be equal to f inverse in this case. So what I end up with is dy over dx is equal to 1 over f prime of f inverse of x. And that's a formula that we can use to find the derivative of the inverse of any function generally, and it does have some other applications. We're not all about that formula. What we're about is seeing how this method works to help us get at what we really want to do here. So let's start by taking a look at the inverse sine and see if we can come up with a derivative. Okay. So for inverse sine of x, since I don't know how to differentiate it, I'm going to say, well, this is the angle that I would get when I get this ratio x. So in other words, if sine of y is my ratio, that should be equal to x. So now I'm going to differentiate this function implicitly. So to differentiate sine y, I get cosine of y multiplied by dy over dx, and that'll be equal to 1. So this is dy over dx is going to be equal to 1 over cosine y. But of course, we know that y is equal to the inverse sine of x, so that tells me that dy over dx is actually equal to 1 over the cosine of the inverse sine of x. So there we are with a composite implicit function. Now, we're going to play a little trick here. Let's remember our first Pythagorean identity from way back when that says that cosine squared of something plus sine squared of something are added together. Whoops, sine squared. That has to be equal to 1. And another way for us to write that is to say that cosine of x should be equal to the square root of 1 minus sine squared x. So that's just a rearrangement of that formula. So what I'm going to do now is I'm going to look at this denominator as being cosine of some stuff, and I'm going to fit that stuff right in here. So this is going to be 1 over the cosine of, and instead of, oh, sorry, I got rid of the cosine already. Excuse me. So it's 1 over the square root of now 1 minus sine of inverse sine of x, and then all of that is squared. But what you should remember from our work with composition of inverse functions is that the sine of the inverse sine, as long as we're dealing in the right range, is just equal to the variable x. So what we have here is 1 over the square root of 1 minus x squared. And that's the formula that we use to say if y equals inverse sine of x, then the derivative y prime, or dy over dx, is 1 over 1 minus, the square root of 1 minus x squared. Okay, let's take a look at another one. Let's try to do this for inverse tan again. So we'll start the same way. Say that tan y has to be equal to x. So then we differentiate implicitly. So the derivative of tan is secant squared of y times dy over dx, and the derivative of x is 1. So a quick division, and we at least have some formula in terms of y anyway for the derivative of tan inverse. Okay, and then we'll do our replacement again. So instead of secant squared y, I'm going to call it secant squared of the inverse tan function. So dy by dx now is equal to 1 over secant of inverse tan of x, and it's secant squared of that stuff. So all that squared. All right, so now we have to come up with a Pythagorean replacement for secant squared in terms of tan. And it just so happens that we have one. So we should remember this time that we have an identity that says that secant squared of any variable is 1 plus the square of the tangent of that variable. Okay, so then I can take my derivative that I have already, dy over dx, and I'm going to turn it into 1 over. Instead of secant squared of theta, I'm going to call it secant squared of tan inverse x here, and that'll just be 1 over 1 plus tan squared of tan inverse. So I'm going to say 1 over 1 plus tan of inverse tan of x, and I can put the square on the tan, or I can say that the whole thing is squared. That's an equivalent way to say it, and it makes it a little bit easier to see that way, that we just get 1 over, and tan of tan inverse becomes just x, so it's 1 plus x squared. So there's our derivative. Okay, so that's a nice tidy one. Let's take a look at another. Let's try the same technique this time, but let's see if we can differentiate cosecant, the inverse of cosecant, or if you want arc cosecant. Okay, so we're going to say that cosecant of y is going to be equal to x. So when I differentiate or take the derivative of cosecant, we should remember, is minus cosecant cotan. So this one looks a little more complicated on us all of a sudden, multiplied by the derivative of y, which is dy over dx, and that'll be equal to 1. So now we have dy over dx is going to be equal to 1 over negative cosecant y times cotan y. Okay, so there's lots of stuff there, but what we're going to do now is we're going to replace our y's again. We're going to replace them with the inverse of the cosecant. So dy over dx is going to be 1 over negative cosecant, and instead of y now, I have the inverse of cosecant of x, and that's multiplied by the cotan of the inverse of cosecant x, like so. Alrighty, so this is going to start off real nice over here on the left. So over on the left business in our denominator here, cosecant of cosecant inverse, we should know now, is just going to be x. So we can put all that together, and we're going to have dy over dx shall be equal to, in principle at this point, 1 over, and we've got a negative, so let's put the negative up there, it doesn't really matter. So we've got negative 1 over cosecant of cosecant inverse is just x, but we still have to deal with this cotan of cosecant's inverse of x. So arc cosecant of x there. So what we have to do is we have to try to find a replacement for cotan so that we can get the cosecant business to disappear like we did with the other stuff. So let's remember we also have a Pythagorean identity for that one. And our Pythagorean identity for that one says 1 plus cotan squared of any angle theta is actually equal to secant squared, or sorry, cosecant squared of theta. Okay, so that's going to give us cosecant squared. So I can replace the cotan squared with, if cotan squared theta is here, that's going to be cosecant squared minus 1. Okay, so then this becomes cotan squared will tell me that cotan theta is just going to be the square root of cosecant squared theta minus 1. So all that stuff is just a little side note to help us get along here. So you see where my substitution is coming from. So this becomes 1 over x times, so cotan I'm going to exchange for the square root of cosecant squared of inverse cosecant of x, and then that is minus 1, of course. Extend my square root out that far. Alrighty, so again, cosecant of cosecant inverse is just going to cancel. So what we get here is negative 1 over x outside the square root of x squared minus 1. Okay, good stuff. Now, so I think what I'll do here is just one more with you. I'm going to do the derivative of the inverse of secant, and then I'll leave 2 of them to see if you can work them out, and then we'll compile them all together. So let's see how this works. So this means that secant y is going to be equal to x. And of course the derivative of the derivative, can't speak today, the derivative of secant is secant times the tan, and then this is implicit, so we need dy over dx, and that has to be equal to 1. Okay. So then dy over dx will be 1 over secant y tan y. All right. So secant y tan y, we're going to replace the y with what we knew we started with. So then dy over dx here is going to be equal to 1 over secant y is going to be secant of arcsecant of x times tan y, and that's going to be tan of arcsecant of x, like so. Okay, so then our derivative, dy over dx, shall be equal to 1 over secant of arcsecant is just x. And so for the tan function, let's remember the identity we had for tan. We said that tan squared theta was plus 1, was equal to secant squared theta. So this time I'm not trying to replace the secant squared here, or secant, I'm trying to replace the tan. So I'm going to say that tan theta is secant squared theta minus 1 square rooted. Okay, so then what we're going to have down here, instead of tan of this stuff, we're going to have the square root of secant squared of the stuff minus 1, like so. Okay, I didn't extend that one far enough either. So there we go. So if we put all this together, then what we have is 1 over x times the square root of secant squared of inverse secant is just going to be x squared minus 1. So in this case, we get 1 over x outside of x squared, the square root, of x squared minus 1. All right? So let's jump to the next page. And this is example 5, so I'm going to leave one for you to do. So let's see if we can work this one through as well. Y equals inverse cotan. So then we're going to have cotan y, cotan y equals x. And so when we differentiate, the derivative of cotan is negative cosecant squared of y times dy over dx, and that's going to be equal to 1. So dy over dx then is the negative of 1 over cosecant squared of y. All right, so now we need a trig identity to replace cosecant. And what we should remember about that one, the one that replaces cosecant, of course, is 1 plus cotan squared theta is equal to cosecant squared theta. Alrighty, so 1 plus cotan squared theta is equal to cosecant squared theta. So what we're going to do with that then is we're going to try to replace the cosecant that's down here. So this is going to be equal to 1 over, sorry, we have a negative in front, so it's 1 over cosecant squared, which is 1 plus cotan squared. And that's of y, which we already knew was cotan inverse of x. And so when we do that, what we get is the negative of 1 over 1 plus x squared because the cotan was squared. So the derivative of cotan then is the same as the derivative, or inverse cotan is the same as the derivative of inverse tan, but it's negative. So they're kind of counterparts that way, and that's what we get for that one. All right, so here's the your turn question. I'm going to let you try one, and all you have to do is differentiate little old arc cosine. So after seeing those 5 or following through, hopefully you can pause the video, or if you have to have a look back, go ahead and see if you can work this one out. I'll jump to the solution, and we'll see that magically we should get here dy over dx equals the negative of 1 over the square root of 1 minus x squared. Now, all of this is well and good. You're probably not going to have to reproduce any of these derivatives on your final exam, but if you're taking the CPT, you might, and it's good knowledge to understand where they all come from and how they all fit together, because that's important for us to understand how we're going to apply them. So I thought this was a good video to do. And let's take a look here. For the key ideas, all I did here was I gave you a summary table of the derivatives of all of the arc trig functions, so the inverse trig functions. And again, I'll give you some pointers on how to remember them all if you have trouble remembering such things. We look at every function and its co-function, and they're very similar. The derivative of arc sine is 1 over the square root of 1 minus x squared, and the derivative of arc cosine, its co-function, is negative the same thing. And notice, if it starts with a c, its derivative is negative. So the derivative of tan was 1 over 1 plus x squared, so the derivative of cotan, which is its co-function, is just the negative of it. And the derivative of secant is 1 over x outside of the square root of x squared minus 1, so right here for secant, and its co-function is exactly the same thing, but it's negative. So those are actually, even though they're scarier looking, they're kind of easier to remember than the derivatives of the original trig functions. There's even more similarities between the functions and their co-functions. Okay. So hopefully that's helpful, and you got a better understanding of how we look at the derivatives of inverse trig functions. And I hope your studying is going well. And if you have any questions, feel free to ask. Post them up on D2L. Thanks.